who would be speaking on some experience on field monitoring of unsaturated soil slopes in Thailand. So Aditi, please.
A very warm welcome to all. It gives me immense pleasure to introduce our first speaker for today, Dr. Apiniti. Dr. Apiniti is currently an associate professor in the Department of Civil Engineering, Kasetsart University, Bangkok. He obtained his BE degree in civil engineering from Kasetsart University in 1999. He then went on to pursue his MSc and PhD in soil mechanics at Imperial College London with the support of the Anand Mahidol Scholarship from Thailand. His research interests include the application of unsaturated soil mechanics on practical geotechnical engineering problems such as rainfall-induced landslides, excavation, embankment stability, bioslope engineering, as well as energy piles. Dr. Apiniti was awarded the Young Technologist Award from the Foundation for the Promotion of Science and Technology under the patronage of His Majesty the King of Thailand. Dr. Apiniti has been the International Secretary General of the Thai Geotechnical Society since 2009 and is currently a member of International Society of Soil Mechanics and Geotechnical Engineering. Currently, he serves as an editorial board member of Journal of Japanese Geotechnical Society, International Journal of Geosynthetics and Ground Engineering, Soils and Foundations, and as a guest editor of Geotechnical Engineering, the SEAGS AGSSEA Journal. I welcome you and thank you, Professor, for your valuable time.
Good afternoon or good morning, everybody, and thank you very much for the very kind introduction. First of all, I would like to thank all the organizing committee for kindly inviting me to be able to join in this wonderful program. So today I would like to talk about some experience on field monitoring of unsaturated soil slopes in Thailand, and the introduction and the outline of the presentation. So first, I will speak about the rationales for field monitoring or instrumentation of slopes in tropical climate like Thailand. And I will try to answer the questions like where to put the instruments. We talk about the new technology called groundwater aeration surveys. And then I will present about various case studies in Thailand, like the criteria for critical water pressure or suction, and the relation between slope movement and suction, as well as the vegetated slopes. And with that, I will conclude. So first, the problem statement. Slope erosion, soil erosion, or slope failure like this happens so frequently in highway, rural road network in Thailand. And of course, these are mostly related to heavy rainfall, and they're becoming more and more increasingly frequent. And this is possibly due to the extreme climate that leading to severe drought that alternated with heavy rainfall, forest fire, and so on. And there are also needs for agricultural land in highlands and in mountainous areas, as well as the encroaching of the poor community in many landslide risk zones. So many farmers, they practice the slash and burn that lead to air pollution, erosion, and landslide risk. This indirectly affect the landslides in the highway and roads going on through this mountainous area. So in Thailand, I think like in many places in Asia, we suffer from the shallow slide or debris flow in the hilly terrains like this. And these shallow slides can be widespread and lead to the debris flow in a large area like this, causing a lot of destruction. But this kind of failure, this kind of shallow slide, can be prevented successfully using vegetation and bioengineering, because in many cases, hard engineering structure approach can be too costly. And also there are needs for providing the early warning system for such rainfall-induced landslides. And one of the requirements is that we like to have the low-cost monitoring system so that we can install as many as possible of these devices in the field. So one of the simplified mechanisms that we commonly encounter or assume is that when the rain falls, rainfall will lead to infiltrations and leading to wetting front movement or the perch groundwater table rise like this. And with the reduction of soil suction or increase in pore pressure will lead to decrease in effective stress and subsequently to the decrease in shear strength and the slope stability. And because soils in tropical area are normally unsaturated, so understanding the infiltration is very crucial. So talking about the soil water characteristic curve, permeability function, and so on. However, in the field, the seepage in slopes can be quite sophisticated. For example, we not only have the rainfall infiltration, but we can also have the exfiltration of the groundwater, from the rock layers to the topsoils, and this inclined seepage in rock layers can happen along the discontinuities. And on top of that, runoff and severe erosion can continuously change the slope geometry, especially at the toe. And after the long drought season, we can have desiccation and cracks, and that can lead to the preferential flow path. So in short, I think for seepage in the tropical slope, the wetting fronts not normally come in terms of the finger flows, for example. So I mean, but in practice, we normally try to use a simplified technique to give the warning, to warning for the rainfall induced landslides. So we normally use the rainfall pattern for the providing the warning as a criteria for warning. So we normally use the combination of the daily rainfall together with some antecedent rainfall. In Thailand, we normally use the 3-day antecedent rainfalls. And the reason is that sometimes we have the delay failure, like this case in Samui Island. Samui Island is one of the tourist destination in the southern part of Thailand, and this failure is actually happened when when there is no rain. So there are some questions like how water can infiltrate the ground and trigger the landslide, how long should we wait for, and how we can give the early warning. So instrumentation and slope monitoring are very important in this regard. So now we are talking about the monitoring or putting the instrument on the slopes, but let's revise or let's recap about the purposes of all this instrumentation in geotechnical engineering projects. So I just would like to review what Dr. Danny Clift has proposed in his book about geotechnical instrumentation. So the purpose of this instrumentation firstly is for safety. So for early warning system. And another thing is for construction project like observational method that pioneered by Professor Ralph Peck, and also for construction controls like foundation in the unsaturated soils. And also the benefit of this slope monitoring is for legal protection for the owner or for the authority of highways, and also for public relations, and for many of us here, as for the purpose of advancing the state of the art. If you are the PhD or master student or professor R&D is very important. So yes, slope monitoring and instrumentation of suction and pore pressure are very important, but it is also important to think about the practical aspect of this as well. So I would like to introduce some of the recent advancements in the slope monitoring system that we developed at Kasetsart University. So right now we have developed what we call the GIL platform. GIL stands for Geotechnical Innovation Laboratory of Kasetsart University. So with the various kind of slope monitoring device that I will introduce in a bit, we transmit the data through, in Thailand is called NB-IoT. So it's one of the popular low power wide area network in Thailand. Maybe you can find your own network like this in your country. And with that, if we send this to the cloud server, and we can do the online analysis or processing of the data and provide the warning criteria. And this platform can be accessed using web application or mobile application on your phone. And if you calculate, for example, the factor of safety or the warning criteria based on the inclination or tilting of the slopes, and give you the notification if any likelihood of failure is going to happen. So various monitoring device that we developed in Thailand is consists of the tensiometers, piezometers, and moisture sensors, and the inclinometers. So just recently we have developed the in-place inclinometer that can be installed in the ground. And this is the rain gauge, tipping bucket, just common tipping bucket rain gauge. So this is appearance of the data logging station. So now I would like to talk about the location, the effective location of the instrumentation. So when we decide to do this instrumentation in the slope, we have to decide about the location of the instrument. However, in reality, the seepage can be very irregular, unlike what you got from the numerical analysis. But the flow can be in the like a finger flows or pipe-like flows or fracture flow. So it can be very difficult to find the exact location of this critical seepage zone. However, the success of the drainage technique for stabilization or landslide warning systems pretty much depends on the location of this instrument. Of course, you can use the commonly used geophysical method like resistivity that is commonly employed in geotechnical engineer, but it still needs some expertise and processing time. So if you want just to go on the size and then just be able to locate the area where there is the seepage, so we adopt the technology developed by Dr. Tada in Japan in 2005. He developed a novel technique for finding the seepage location based on what they call the groundwater aeration sound. And we see that this is a quick and convenient method to find seepage in the field. It can be even used by non-experts, but with some training, and is quite suitable for practical work that require immediate information on seepage location. Like if you want to determine where to put the piezometer or put the horizontal drain, I think you should know where exactly to put where the groundwater comes from that part of the slope. So this how the device looks. So the device uses the ultra sensitive sensor. So it's just like the accelerometer or a microphone, if you like, for picking up the ground aeration sounds. And with the large amplification, we could hear that sound and we could see the amplitude of the sound or the loudness of the sound in the numeric terms. So, and these sounds actually comes as a result of water seeping through the soils. Once water seeps through the soils, air will be pushed out, resulting in what they call the bursting of the menisci water, or this kind of water menisci is being pushed out. So this air bubble will be burst. So this sound level in terms of acceleration will be calculated and processed, shown by just only the device index unit called the value. Unfortunately, due to technical reason, I was trying to play this sound, but it doesn't work. But I give you this link here where you can just log on to this website, and then you just press this button and you can hear the sound for yourself later on. So, and with this the value, we can read the acceleration number from this chart provided by the manufacturer. But of course, we would like also to relate this d value with the suction or with the pore pressure, which I will introduce to you, just to show you the typical results and the field application of this device. So, for example, on the hill slope like this, where there was the landslides happening here, and right after the landslide, there could be a scar like this. but maybe after many years, all the vegetation is coming up, and you cannot hear the you cannot see the scar anymore. So these studies, they just walk on the top of the hill like this and listen to the sounds, and they could hear a very loud sound just on top of the scars. And we did a similar study in Thailand, in Uttaradit, in north of Thailand, where we look at Google Earth, we could see the scar, the location of the slice. But when we did the monitoring, we didn't see the scar. And then after the processing, we could see that the high level of the sound actually coincide with the location of the scars. But of course, there are some noise during the measurements, and we have to deliberately omit these results from the interpretation. And another size that we have experienced is on the cut slopes in Surat Thani, in the southern part of Thailand. This is the cut slope that suffer from deep-seated slope failure. And this failure was actually controlled by some kind of rock discontinuity, and is also suffer from severe erosion. The geology of this site is that of sedimentary rocks, including sandstone, integrated with siltstone with some distinct failure plane. So this is the picture when we did the gas survey. So you have to walk along the slopes, and then push the sensor onto the grounds, and then listen to the sound of the groundwater aeration, and then just write down and then put these numbers along the line. And then we could actually see that the location of the gully is actually coincides with the location where we could hear a lot of seepage sounds. So yes, in practice, if you don't have this device, but it's quite intuitive, to think that along the gully there will be a lot of seepage anyhow. And we also combine this with the geophysics test, and this result from gas survey actually in a good agreement with the geophysics studies. And after this, we could develop the water flow on seepage conceptual model like this, that we have the rock fractures, and once the seepage flow along the rock fractures, and then we could hear a very loud sound, especially along line 1 and line 5. However, below the slope, below the road here on line 2, line 3, and line 4, the sound was not as loud as on line 1 and line 5. So this is quite counterintuitive when you think that at the toe or the lower part of the slope, you will expect to hear more louder sound of the seepage, or more critical seepage sounds. And one of the useful tips when after we conduct the study is that we found that the cracks along the road, the small road here, is actually coincide with the level when the sound level is quite high. So one thing to take home is that if you want to quickly locate the area of the high seepage, yes, that's the location when the damage to your road appear, just like this. And the orientation of the cracks along the roads is actually aligned with the orientation of the rock fracture planes and the high sound level of the seepage, for example. Like this crack, along this crack here, you could hear a very loud sound of the seepage. So another attempt that we have tried is that we try to correlate this water pressure with the groundwater aeration sounds. So I would like to explain about this case studies that we put the water pressure and suction monitoring device on the vegetated soil fields in Nakhon Nayok. So this is the failed slope that has been reshaped and regraded, and put some vetiver grass on it. And we put the KU in kilometers in the slopes, because the slide is quite shallow. So the depth to the bedrock or to the slip plane is about 3 meters. So we do the borehole, and then we put like a rough steel bar to fix this PVC pipe to the firm base. And then we put the kind of accelerometer on different points along this pipe. And then we could actually observe the movement. So this is a typical result of the water pressure and suction in Thailand. And during the rain seasons, the suction can be in the order of maybe to 0 to minus 25 kilopascal of pore pressure. And only during the heavy rainfall intensity. So these bar charts represent the rain intensity of at this point is more than 100 millimeter per day. We start to have some positive pore pressure, just like this. So suction is important, of course, but in the critical time when the slope start to move, it only moves when you have the positive pore pressure. And of course, during the dry season, the water pressure decreasing, suggesting you have the suction, and then it keeps decreasing until 100 kilopascal, until what we use is the low capacity tensiometer. It doesn't function anymore. So it means that the tensiometer needs frequent maintenance if you want it to function properly. But in some case, even without de-airing the device, we can still keep using it for the next year. But the best practice is to remove it and to resaturate it. So we compare the movement from the inclinometer reading. So we plot in terms of the shear strength. So you can see the movement of this that correspond to the daily rainfall and correspond to this pulse of the water pressure. So this is like the groundwater level rise during this time. And we try to back analyze this or simulate this using the finite element program called DAXA, developed by Tokyo Institute of Technology in Japan. We use a simple drag and paper model, and we compare the shear strength of this. So quite a good comparison. The simulation under predict the shear strength, but of course, if we change the modulus value of the soil, we can get a better improvement. But this point just to show you that the movement of the slope start to happen when you have the positive water pressure. And with the simulation, we could use this shear strength at the failure point from the simulation, and use this shear strength as the threshold that we develop for the inclinometer reading. So we could have the threshold value for warning system, like based on the rainfall intensity, that could based on the past event of landslides or simulation using the many finite element software for seepage. And we can have the water pressure. It can be used in terms of the RU or coefficient of pore pressure and shear strength. And we could develop some kind of alert, alarm, and action based on this threshold. Right. And now I would like to talk a little bit about the groundwater aeration again. So just now talk about this D value that is actually the level of the loudness of the ground aeration sound. So we try to correlate this D value with the water pressure, and we could hear the groundwater aeration sound or the D value, when we have some suction, because the seepage can be happening in the unsaturated zone and the air bubble bursting and so on happening. However, we find that this technique, this gas technique or groundwater aerations depends on the timing, on the time when you do the survey as well. So when we go back to the site at different times and different size, we have different correlation, and that's due to the different in background noise and different time and so on. However, in the relative term, we could find that, okay, especially this area is the more critical zone than the other zones, for example. So we have different set of the correlation between the values and the average water pressure in the slopes. So this observation is, of course, is site specific and should be used with caution, but at least it gives us some idea, if you like, that if you have just only this groundwater aeration device, we can go to the site and just put it on the soil surface, and we could guess how much seepage there would be on the slopes. So we did some SWOT analysis for this gas survey. So the strength of this device is quick interpretation, but the weakness is that it's only limited to 10 meter deep. And the opportunity is that we have a great potential for the application where you just need a quick interpretation. So it's very useful in practice. But the threat is that this device is quite difficult to use, and we cannot use it actually during the rains with area with high noise, with a lot of cars going around. It's very hard. It's impossible to use this one. But it's quite simple, and it's very simple to use, and it's a great cost saving, and especially when you do the drainage installation, something like that, horizontal, what we call it, the precise slope stabilization. Now I'd like to move on to another experience of ours on the critical water pressure that we use as a criteria for the early warning. So I would like to talk about this particular site in Uttaradit province in northern part of Thailand. And this area actually suffered from the rainfall this landslide quite some time ago in 2006 that triggered by, torrential rain, 400 millimeter of rain per day. And the major mode of failure is shallow slip, like in the photo. The geology is Carboniferous Permian siltstone and mudstone with fold structure, and the depth of residual soil is relatively shallow. And the other contributing factors include the degradation of this, what we call argillaceous material, and there are some deforestation as well. And we put this instrument along this line here. And the soil profiles consists of this topsoil, residual soil, and completely wetted rocks. And this kind of profiles due this permeability profile like this. So we have quite a loose topsoils with the permeability in order of 10 to minus 6 to 10 to minus 4 meter per second. But the value of the permeability vary quite widely along different locations, the slopes. But the permeability reduces with depth and become quite low at the bedrock about 2 meters. So clearly, if the rains keep, supplying the water to the slope, infiltrating the slopes, if we have the perch water table at the bedrock. So we install these tensiometers along different levels on the slopes. And this is the typical value of the tensiometer reading. So we have some suctions in the order of 10 kPa, 10 to 20 kPa during the rain. And then during the dry season, we have no rain at all. And the water pressure reduced down to the point where the tensiometer start to cavitate at minus 80 kPa. So again, we need the frequent maintenance of the tensiometers. However, during the rain season, when we have the heavy rainfall like this, so nearly 100 millimeter, in this case is about 70 millimeter per day. Okay, we could not observe the inclinometer reading here. And when we look at the water pressure at this particular time, the water pressure is still quite small. It's only 0.5 to 1 kPa. It's only, so it's equivalent to like 10 centimeters of perch water table. Is quite low. However, we also investigate about the failure mechanism of the slope, and I mentioned about the argillaceous or degradable material of the residual soil derived from the mudstone and so on. So we did a simple experiment here when we actually look at the effect of wetting and drying. First, we did the test on the intact samples, and we could see that the cohesion or effective cohesion actually increased with depth. So the smallest cohesion is about 0.3 meters. At 0 meter deep, we have quite high cohesion, and that's because of the roots, because in the sample, they have root reinforcements due to the topsoils. So we look at the effect of the drying and wetting. So we simulate this in the lab, like 3 days of soaking of the sample and plus 1 day of oven dry. We call this 1 cycles. So we put the sample, impose it over 5 cycles of wet and dry. We could see that the cohesion value of the soil actually decreasing with the cycle time of wet and dry. But this is a small direct shear test. We could have some cohesion intercept here. But we could say that the C dash or effective cohesion reduced by 50 to 60%, while the angle of shearing resistance phi dash relatively unchanged. So we could see the implication of this kind of pore water pressure rise and then the wetting and drying in the slope stability by using a very simplified model of infinite slopes. So you can see that for the slope angle of 25 degree and 45 degree, what we call the threshold or the critical factor, critical pore water pressure here is a positive value. So the pore water pressure has to go to the positive value to bring the slopes down, But of course, this is because we have some cohesion of the soils. And then at a greater depth, when the thickness of the soil is larger, we need to have the higher pore water pressure. Okay, so this critical pore water pressure relate to depth as well. And then we also looking at the effect of wet and dry. We could see that when the factor of safety equal to 1, this we can obtain the critical pore water pressure or the threshold. And after, about 5 to 10 cycles of wet and dry, so if the soil is degraded, maybe by deforestation, by forest fire, or by clearing of the land, if there is no cohesion, maybe losing of the vegetations or severe wet and dry, severe climate, for example, we have a sharp decrease in the cohesion and sharp decrease in the factor of safety. Okay, so my point is that not just only loss of suction and increase in the pore water pressure or the groundwater table, but the severe wet and dry can lead to slope failure like this, or clearing of the trees lead to failure like this. Okay, and some recent, it's not so recent, it's 2010, I think. Yeah, we have the event of the flash flood event here. So this is the reading during the not normal time. So we have the negative pore pressure like this, minus 10 to 0. And during the flash flood, we were lucky to be able to monitor the slopes on the side of this flash flood here. So we could obtain somewhat the soil moisture or the water pressure profile on the slope during the flash flood. But it's only the flash flood, no slope failure. So this is the water pressure profile during the flash flooding. But it suggests that this correspond to the like a hydrostatic profile, but it's a slope. So this profile corresponds to the seepage down slopes. So the soil is maybe saturated, and then there is some flash flood happening. So the factor of safety is still more than 1, still more than 1. So the pore water pressure has to rise above this, has to rise to me bond it is to bring the factor of safety to 1. Now I would like to move on to another part about the bioslope stabilization. So we know that in many cases, hard engineering structure may not be able to withstand the force of the nature, and a hybrid approach, when we use the plants in combination with structure, is more effective. Like this picture, you have this kind of a short grid with the soil nail, but it cannot withstand the seepage force and something like that. The retaining wall just crack like this. So we like to use that we call the soil bioengineering, which is defined here by Soter in 2002 as a sound engineering practice that we have to integrate ecological principle to assess, design, construct, and maintain living vegetation system, to repair and to protect, enhance healthy function of the slope. So in Thailand, we use like a vetiver grass or soil bags with live stake and so on. So this tell you the timeline of the bioengineering in Thailand. We use vetiver grass quite frequently, quite widely, but we also use the erosion control blanket, control lock, and flap soil bags, and so on. And recently, we use these flap soil bags with the micropies. So the research approach is that we combine field observation, laboratory, numerical modeling. So field observation is very important. So I would like to relate this bioengineering to the field monitoring part of my talk. So firstly, which species that we can use as a bioengineering? So we investigate various kind of the live stakes. So I think I won't have time to go into the detail of all the species, but I just want to point out that this fast-growing species, or what we call the pioneer plant, is very useful, is very effective as a live stakes. However, we find that the growth rate or the effectiveness of these pioneer plants depends on the suction or on the soil moisture condition, because we also monitor the growth rate of this live stake by monitor the length of the longest branch of the stake. We find that once the suction condition in the slopes actually go beyond 30 kilopascal, like during the drought season, this live stake growth rate start to drop, and some even die. So that in order to plant tree successfully, you need irrigation or watering system. And also we look at this root soil mechanics as well. So this is biomechanics of the roots with the soil. So when we think about the contribution of the roots to the soils shear strength, it can be in terms of the root reinforcement like the CR. So we have the simplified the model for the root reinforcement as a root cohesion. And roots can also affect the water pressure by infiltration and transpiration. So root can affect the infiltration by changing the soil water characteristic curve or permeability function of the soil, but it can affect the transpiration by inducing the suction in the ground. So it can decrease the water pressure. So when we look at the simple mechanistic model for root reinforcement like Wu 1979, so we can calculate the root cohesion based on this tensile strength of the roots and the amount of the roots in the soil. So at Kasetsart, we also use the large direct shear test to be able to test the root contribution on the soil in both unsaturated and saturated condition. And we could develop a model to predict the root cohesion based on what we call the site root area ratio. So if you know the root area ratio in the site, we can predict the CR or the root cohesion. So we could adopt this technique in the field as well. So we could put what we call the mini rhizotron, which is a transparent tube on the slopes, and then we can monitor the root area ratio in the ground, and we could also monitor the suction, but it's only the point-wise the measurement, so it's only at one point. But of course, we could kind of extrapolate this kind of point measurement by using some image analysis of the whole slope, something like that. So in this case, we use what we call the jatropha live stake or the brush layer. So the live stake is laid kind of inclined direction, perform quite well, and we observe the root concentration in terms of area ratio in the ground. And with the root sketch like this, we could calculate the root area ratio, and with the relationship between root area ratio and cohesion, we could estimate the root cohesion in the field. And with the root cohesion, we could estimate the factor of safety. But of course, the factor of safety or the contribution of the roots depend on the suction, depend on the moisture condition as well. So this factor of safety that relate to roots are also related to the suction condition in the field. So soil suction is not only important for early warning, but it's also important for calculate the contribution of roots on the slopes. And another thing where slope monitoring can be quite important is when we evaluate the erosion control products like the slope mulching. We know that benefit of soil mulching include prevent erosion from direct raindrops impact and prevent soil surface drying, increase soil nutrient, and so on. And we have various techniques like hydroseeding, 3D netting, erosion control product. And in Thailand, we have this test site in Doi Intanon that suffer from the shallow movement. Previously, the slope was stabilized using a shotcrete, and it failed. And so we use this erosion control device with the horizontal drain. So we install some water pressure monitoring device here. Okay, this is the location, the horizontal drain. I would like to show you the soil cover system that we use for this remediation. We have various techniques like the erosion control blanket on top of the clay sorting. So we have the fine grain on top of the coarse grain. So it could actually act as a capillary barrier of this on the slope as well. And section B have soil log and clay sorting, but without the soil blanket, erosion control blanket. And D we have soil blanket and soil log and geocell, erosion control mat here. And we install in total 60 KU tensiometers on this part of the slopes. And the monitoring of the rainfalls show here that we have various times when the maximum daily rain is more than 100 millimeters. In Thailand, the usual threshold when we issue the warning for landslide is 100 millimeter per day. So on this day, we have quite a few days when we have to issue the warning. And after this first time evaluation, we find that plot A is better than other plots. So this is just like the visual inspection. And however, the second observation after the torrential rain in Thailand, all the plots is actually fail, really, but fail from the shallow slides and so on like this. And we monitor the pore water pressure. So we could find that this is the pore pressure contour during the dry season. We could see that there is a saturation point at the toe. So the pore pressure is positive at the toe. However, during the rain season, after heavy rains, the high concentration of the seepage or the high water pressure zone is happening on the top here. And we also try to do the simulation using some two-dimensional finite element software like a W. We could get a good agreements, but mainly only at the 0.5 to 2 meter depth deep. And at the 3 meter deep, we find that we still struggle to have the good agreement with the simulation. And we think that this may be due to the 2D effect as well. So after the very long term, we find that the slope has been fully vegetated like this. And I'm afraid I have no time to talk about this point, but I just would like to point out that after the slope has been fully vegetated, the root zones will play important role in affecting the permeability and soil water characteristic curve of the soil. So if we would like to accurately the model the slope behavior, you need to take into account the changing of the vegetation in the slope with time as well. So I'd like to finish the case study by showing this case of using the micro screw pies with the flap soil bags and with the live state vegetated soil bags like this. So we concerned, this is the first time we use this technique in Thailand. So we concerned about the performance of this particular technique here. So this technique is a lightweight technique when we use the micro pies installed to only about 2.5 meters. So it stabilizes the shallow slice, and we have the flap soil bags to prevent the overflow or surface erosions or over the road, and we have this kind of live stakes to act as like a natural drainage, like a natural horizontal drain and the root reinforcement with time. So this is the location of the instrument that we put. Again, we use the groundwater aeration sound to locate the critical zone. We put 9 instruments all together at 3 locations on the slopes. So first, let's have a look at the change of the appearance of the trees or vegetation with time. So this is the picture before the stabilization and after the construction complete, and this 1 year after the construction. So we could see that the trees start to grow. Now let's see the monitoring results. So the tilting degree, this is the tilting of the screw pies, is very small, is even less than 0.1 degree. And the soil moisture, the soil moisture is actually lower in the lower part. And we have, if we look at the water pressure, so we have a negative water pressure again during the dry period, and during the rainy seasons it start to go up like this, and again the water pressure is in the magnitude of about -10 to 0. And one of the point that I would like to make is that, with the tensiometers, it's very good to have the measurement from the tensiometers, but in the remote area like this, it's very difficult to go back to the site and do the flushing or maintenance of all this. So from this point onwards, we decide that even if the tensiometer stopped working reliably, we could actually make use of the soil moisture sensors, and we could have the correlation. It's just like the local correlation between water content and water pressure, or the local soil water characteristic curve, if you like. So in the long term, we could rely on the soil moisture measurement to calculate the like a real-time factor of safety. So with this, I would like to conclude that slope failure and erosion is more severe due to the climate change and increasing infrastructure in Thailand. And water seepage in slopes is so sophisticated in the Vados zone, not just only because of the suction and the unsaturated soil property, but due to the geological heterogeneity, rock fracture, and so on. And the critical job is that how to find the suitable location to install these instruments. And we find that the major slope movement normally take place when water pressure is positive. But of course, monitoring of soil suction and water content is quite useful. It's also useful for early warning of the slopes. And also not just that, it's also useful for bioslope stabilization if you want to have the control irrigation in order to make your plants survive and be able to stabilize your slopes. So if you'd like to read any of these papers, please feel free to send me emails. And then I would like to acknowledge various organizations. And with this, I would like to thank very much for your attention. And will be the question and answer. Thank you very much. So hello.
Paniti, I can hear you well, but it seems that we've, I don't know whether Ashutosh is.
I think we lost connection with them. So
I see. Thank you very much, David. I thought I spoke for 1 hour and no one could hear.
No, we heard it all. Thank you.
Okay, thank you.
Let's. I don't know whether we can see any questions. Let me just.
It's okay. Yeah.
Can you hear me?
yeah, there is question in the chat.
Okay.
Yeah. Apiniti, can you hear me? I'm back now. Sorry about that. And you can hear me, right?
Yes, I can hear you. Thank you.
All right. Sorry about the network issue. Actually, just at the end of your lecture, something happened with the network. So yes, we did not miss anything of your lecture. So don't worry about it. That spoke for 1 hour and nobody could listen.
All right. Yeah.
So what I was saying, thank you very much for the wonderful lecture and taking us through various techniques that you are using for slope protection and as well as the monitoring technique. So it was really wonderful to see that so much of technique, and we understood yesterday. Samprada also highlighted that in the remote location, it is really difficult to do monitoring, and there are a lot of challenges that we face while we go for monitoring in the remote locations. So yes, it is really a commendable job, because we always face a lot of challenges once we go to the field that we cannot think in the laboratory or the computer simulation that we do. So a wonderful job, I must say. And so I have one question, and then I would take up some of the questions if it is from audience side or the panelist side. So one question is related to, you have shown the result for oven drying and wetting that you are doing in the laboratory. And so like you did it for on undisturbed soil sample, or it was already disturbed soil sample?
It was on undisturbed intact soil sample. So we could actually, we expect to have some kind of weak cementation on the soil. So we suspect that these cycles of wetting and dry would actually destroy this kind of weak cementation. Yeah, and we suspect that this. Yeah.
Okay. And how did you decide what should be the rate of sharing?
The rate of sharing. We actually, of course, for the drainage, for the drain saturated test, we rely on the Bishop and Henkel criteria, like the classical, like in many soil testing textbook, and that.
Okay.
And for the unsaturated soil, because we did what we call the constant water content test, so we not too concerned about the rate of shearing. So, but we did try the various shearing rate, that it doesn't affect, the measurement of the pore pressure and so on. Yeah, but as I told you that the unsaturated testing is important, but we did the constant water content, so doesn't matter much for the shearing rate, in my opinion.
All right, wonderful. If there is any question from the panelist side, then the panelists can directly unmute themselves and please ask if there is anything.
I saw the question in the chat. Can I answer it?
Yes, it would be great. Yes.
Yes. How soy bags are anchored. These soy bags are called flap soy bags. So these are extended part of the plastic sheet. So it's just like almost like a reinforcement, like a geogrid or something like that. But it's just a extended plastic sheet on the back and on the sides. And the adjacent soy bags would actually on top will impose the weight on the top of each adjacent bag. So it's just like the anchorage of the bag. But actually, we can also use many kind of geosynthetic reinforcement with this bag as well. But the purpose of this bag is to use with the vegetation. So we use it in the remote place, so we cannot use a lot of machinery and so on. So yes, we have what we call the flap soil bags. And another question regarding the durability of the bags. Yes, this bag is a special bag, so the manufacturing company put some UV resistant substance in it. So we have did the test. We collected the bag and move it back to the lab and do the puncture test and tensile strength test. And after 10 years, I think it's still quite good condition. It's still quite good condition. So yes, and I think that's the reason that we use the vegetation with this bag, because after the vegetation provide the full coverage on the bag will not suffer from the UV light, and the plastic, it will last very long time in the field. Okay. I think that would be all the questions. So thank you very much.
There was one more question.
Oh, based on what criteria did you select the duration of wetting and drying cycles? I have to say that it's arbitrary. So we just do what is conveniently done in the lab. And we could actually just say that, okay, this kind of oven drying will be like the extreme drying in the field. But of course, as you know from the field monitoring results, the actual drying in the field is not like the oven dry in the lab. So this, like what we did in the lab, is the extreme case. But it allow us to maybe to guess or to predict what would be the likely failure mechanism of this material. Yeah, I hope that answers your question.
Okay, we have one more question from Kedar Birit, and he's interested in knowing that was the degree of saturation in specimen was 100% to simulate the condition during rainfall of rainfall during direct shear testing. So during direct shear testing, have you considered 100% of saturation?
I think it's a good question, really, but it's not strictly needed, because in the direct shear, what we call it a soak specimen, and we find that, because of course after the test we took the sample out, measure the volume, measure the moisture content, so we could calculate the degree of saturation. Sometimes it's almost like 100, but sometimes it's below, is 80%, 85%, for example. Oh, so I mean, but the reason for this is a natural intact specimen. So it could include some organic matters that can be like the hydrophobic behavior. So it's very hard to fully saturate the specimen unless you have the triaxial system, triaxial apparatus to be able to impose a back pressure. But if you do that, I think it would not necessarily represent the field condition, because in the field condition you won't have the back pressure to saturate the specimen.
Perfect. Thank you. And we'll probably take the last question, and this is from the audience who is attending from IIT Mandi. And so please go ahead.
Thank you, Dr. Pinti, for the wonderful presentation. I want to know how the DAFT decided for the placement of sensors in the field. So, like, what is the criteria for that?
So the location where we should install the instruments, right?
Yes.
Yeah,
Like,
for
under the ground level, like the depth under the ground level where the sensor is placed. So how it is decided?
or the depths, you mean the depths? Yeah, definitely we have to look at the ground profiles. And you need to have the questions that you would like to answers first before you plan the instrumentation. So like for example, you want to see the movement of the infiltration, and you want to provide the early warning of the slope movement. So in that case, you should put one instrument on the slip plane, and you should have the maybe another soil moisture or the tensiometers well above that point, so that you can see the infiltration or the movement or the movement of the wetting fronts, and maybe one on the crest, another one in the middle, another one in the toe, for example, if you want to see the distribution of the pore pressure in the slopes. And also longitudinally along the road, maybe you have to look at the topography of the area, because the slope the water will concentrate on the depressed zone, the lower zone of the valley or the erosion bowl, for example. Yeah, I hope that answers your question.
Yeah, thank you, Dr. Apiniti. And that is all the question that we have for the time being. And of course, I would urge audience, or the participants, if there is any question, then that can be emailed based on the contact details that we have shared. So thank you very much for the wonderful contribution that you have made. And so thank you. And then we will now move to the next presentation that we have. And again, we have Aras here today. And with Aras, Faris would be also speaking. And Aras, like yesterday, we have already introduced Aras, and you all know Aras now, and based on the wonderful presentation he has given yesterday. Besides the numerical modeling and the constitutive modeling experience that Aras has, he also have experiences of field monitoring for countries like Malaysia, South Africa, or African countries like Ghana, Tanzania, as well as in England. So today Aras would like to give a brief background about how field monitoring protocol would be done, and then the Faris would be taking up, and then he would be speaking about the field monitoring protocols that have been adopted in Malaysia. And so, Aras.
Hello again. Good morning, good afternoon. Let's please tell me if you can see my presentation and you can hear me. I don't want to get panicked like Dr. Apiniti at the end of my lecture. Please tell if you can see my screen.
Yeah, you are very much audible, and yes, we can very well see your screen.
Okay, wonderful.
Yeah.
So my presentation today won't. Actually, thanks for your kind introduction again. My presentation today won't be as long as the my presentation of yesterday. I think I made you bored enough yesterday, so I will make it quick today. So I'm just going to share some of our experience with the field monitoring in one of our sites in Africa, and I will explain how we did it, and then after that I will Faris will take over, and he will talk more in details about their experience in field monitoring of slope in Malaysia. So the project I'm going to talk about is called Transport Africa, and basically the title of the project was Sustainability and Resilience of Transportation Infrastructure in African Countries. So I joined Durham University in 2018, And I had a chance to work with wonderful people there. I had the chance to work with Professor David Toll, who you met yesterday. So I learned a lot about unsaturated soils there. And then, well, that was the time I could also meet Dr. Ashutosh, and we keep working together since then. During that project, so we collaborated with excellent researcher from Africa, from different countries, so people from KNU University from Ghana, people from Tanzania, from a company called Nairo and Associates, and also people from South Africa. So, and we studied basically these principles of unsaturated soil mechanics, try to understand it if they can contribute to basically performance of the roads and railways in these countries. So this brings back some memories from those days. So on the top left, you can see us having a meeting with specialists and experts from road authorities, from road sectors. You may recognize Professor in the middle of the picture. Ashutosh and I are standing also behind. It looks like it was many years ago, a time we could get together and we could like enjoy in-person meetings, but it was just maybe 3 years ago. And the bottom picture on the right is one of our site visits in South Africa, the railway we worked on during the project. And Dr. Kumar is in the center, if you know him very well. So the project was about understanding these effect of climate. So this is what we have been trying to explain yesterday, and also we're trying to explain it today as well. So the effect of climate, these precipitation and basically evaporation cycles that all these geostructures above the water table are subjected to. So the effect of this environmental load on the performance of road and railways in these African countries, in Tanzania, Ghana, and South Africa. And the idea was to understanding if the soils, the compacted soil used there as the formation layers of the road and railway, can deteriorate or can degrade on their cycles of drying and wetting, how the suction changed there, how the water content changed there, and if these sort of variations are responsible for these sort of damages you see in these pictures in the rural roads and railways in these countries. So that was the aim of the project. So one way to do it, as we talked yesterday, was just we can do tests in the lab. We can understand how suction change, water retention curve, the relation between suction and saturation degree, for instance, and then on the other hand, how suction changes shear strength, how suction change permeability, all these effects we can do it in the lab, but of course, we have to see what happens in the field. So, and one way to do it, of course, is field monitoring. Dr. Apiniti explained a lot of interesting experience in Thailand. So we try to do there in Africa, in these African countries as well. We try to monitor the interaction between climate and basically soil in the soil used in roads and railway. So the first thing is, of course, making a sensor network to measure soil atmosphere variables. So atmosphere, it means that climate, it is meteorological variables. So we use rain gauge, we use their temperature relative humidity sensor to measure basically these two variables, rain gauge for the rainfall measurements. There are other meteorological sensor types like for atmosphere pressures, for radiation, or all this, but we use only these two sensors in our project. But the other side is, of course, measuring soil variables. So we used different type of sensors to measure soil variables. We could measure displacement, we could measure deformations, different sensors to measure deformation, but because the type of roads we were working on was basically rural roads with low number of basically traffic loads, the focus was the effect of changing of the hydraulic properties. So we didn't measure any deformation, so we measure only the changes in the water content and suction. So I'm going to just introduce just very briefly how these sensors work. So the one variable, of course, in the soil, as we've been talking about, so is water content, volumetric water content, saturation degree, any sort of water-related parameter. And we use this sensor called the 5TE, developed by Meter Group, which are called like something like dielectric constant sensors. So they measure dielectric constant of the soil, which is basically the ability of the soil to store electric charge. And fortunately, there is a good relationship between this dielectric constant and volumetric water content. So it can measure volumetric water content indirectly. It quickly measures the variations of water content, volumetric water content. Installation easy. These 3 prongs help us to insert this into the ground. But the calibration is required. So we always need to calibrate this based on the changes in the water content of the soil before using in the field. So these are different type of sensors, moisture sensors, we call them. So 5T, which is shown by the red. Then we have a blue TDR and ML2X. So there are different type of dielectric constant moisture props. We have calibrated them against the volumetric water content. In most cases, it seems that an equation given by top works with these sensors, but of course you have to check it with the type of soil you're dealing with. It is sometimes it is not as straightforward as it looks like here. The second sensor is MPS6. We use that to measure suction. It is again developed by Meter Group. It is again, you can see at the tip of the sensor there is a ceramic peristone. So where when it is inside the ground, the water content of this ceramic stone changes. So when it changes, the dielectric constant is measured, and from dielectric constant measured, the water content of the porous stone is measured, which gets into equilibrium based on the suction of the soil. Of course, when we put all these sensors in the ground, so everything we measure in the sensor is just representative of the values in the soil as they get into equilibrium. So it measures the dielectric constant translated to water content, and then there is this equation given by the basically manufacturer of the company that relate the gravimetric water content to suction. So it translated again to suction. Again, indirect measure of suction from dielectric constant to water content and from water content to suction. Installation is easy. You can bury it in the ground. You can leave it forever. And the measurement is just a bit delayed sometimes because of the equilibrium takes time. And the calibration is difficult. So you have to trust this curve given by the manufacturer. And the last sensor I'm going to introduce is high capacity tensiometer. You have heard about it yesterday. You heard about it today. So this is very probably more the most the tensiometer that we can trust most, because it measures negative pore water pressure directly. So it is direct tension of the water. So we have this water reservoir behind or inside the sensors in the high capacity tensiometer that goes under tension when it is in contact, when the sensor is in contact with soil. So it measures negative pore water pressure of the soil, which is basically suction. So installation in working with tensiometer in the lab is quite easy. It is simple. We can fit it in any equipment. I think Ashutosh showed you how we fit it on honest to extra samples yesterday. In the its application in the field is challenging, and the challenge is just we have to install it in a way we can remove it when it is needed, and when it is needed, when it cavitates. So there is a limitation on the range of suction measurement. I think Professor Singh showed you at early days. So it was like around 80 kPa, 90 kPa suction. Then I think advanced high capacity tensiometer like the one that has been developed at Durham could measure to up to minus 1.5 negative pore water, which is minus 1.5 megapascal, basically suction up to 2 megapascal. But recently we developed another tensiometer, another high capacity tensiometer that can measure to up to basically 3.5, around 3.5 megapascal of suction. But if we exceed these limitation, we have to remove the tensiometer from the site, bring it to the lab, resaturate it, and then put it back in the ground and in the site again. So because of that, we have to have some sort of installation tools to make it. But the measurement is quick, and it is basically direct measurements of suction. So now let's have a look on what we did in one of our sites in Africa during our Transport Africa project. So we basically instrumented 4 roads and a railroad, so 5 sites. I'm going to show you one experience in one of our sites. So the idea was just to instrument a low volume road. So you can see it is a sealed road. So it means at the surface, there is a surfacing layer that probably should basically ideally prevent the water ingress from the top. So it should be perfectly impermeable from the top. Then we have shoulder on the left and the ditch where we put these pole, and there is an enclosure where the data logger, when I was talking to the when I was talking about sensor network, all these sensors need to be connected to data logger. So there is a device that we connect all these sensors to collect the data. So it sits there, and we have a rain gauge and our weather station on the top of the pole. You can see we instrumented the sensor basically under the outer wheel and under the inner wheel of the car, so close to the center, close to the shoulder of the roads, so at different depths. And this is how we managed to do it. So we basically excavated the road, excavated a trench or a ditch across the road from shoulder to the center, as you can see in this picture. We embedded the sensors inside the body of the inside the wall of the excavation trench, and then all these cables you can see there went into the tubes on the right figure, and then we compacted the soil again at natural water content, and we basically rebuilt the road. So everything is basically embedded and buried inside the road. And then what you can see there, if you go to the side, you can see only this station, so where all the sensors are connected to. So that enclosure at the bottom is just where the data logger is and where the sensors are connected. Basically, we collect the data there. For tensiometer, as I said, we have to be able to remove it. So we developed these pipes at Durham, and we decided to only measure suction at the shoulder, so at the outer wheel line of the road. So these pipes, we installed them from the shoulder, we pushed them into the roadside, and we tried to get to the same depths and positions of the other sensors. So these are basically the pipes and tensiometers that we used to measure suction in this road. So this tensiometer basically goes inside the pipe. So if during the measurement we see that it cavitates and it needs to be taken out, so we can remove it from the pipe, and we, after resaturation, we can bring it back and then push it in the pipe again to get to the same position. But now let's look at some of our data from this site. So rainfall again, so rain gauge, this tipping bucket rain gauge, Dr. Apiti explained it nicely. So it tips with the rainfall, and based on that we get some bars, some values for the rainfall. So in terms of millimeter, on the right axis you can see rainfall measurement hourly, so during these periods, so from July to April, and these blue bars are basically the rain, correspond to the rainfall events occurred during that period, and it is shown on the right axis. So the measurement of water content, volumetric water content from 5TE, installed at the outer wheel of the car, so just close to the shoulder. You see the variation of volumetric water content there at 2 depths. So you can see how responsive these sensors are to the changes of volumetric water, to the rainfall basically events. So a lot of variations during the rainy seasons, but in between, so when there is no basically rainfall, when there is a gap in the basically in a gap in the rainfall events, so we can see that the volumetric water content reduces a lot. So these values are shown on the left axis here now. So the volumetric water content reduces, you see, yeah, you can see here now the drawing occurs with the prolonged drawing period. So the water content reduces a lot, and then There are some spikes that respond to that are response to these single rain events during that dry period, right? So the volumetric water quickly increases on the shoulder. But when we compare it to the volumetric water content of the center, you can see that the variation is not as significant as the other case. So we don't see much spikes during the drying period. The volumetric water content again reduces, but it's not as significant as the variations on the shoulder. So you see that the variations of the volumetric water content are smaller on the center of the road. But let's have a look at the suction variation there as well. So suction on the left, you can see that during the initial period when there are a lot of rainfall events, so during wet season, so basically suction remains zero. It means that soil is almost saturated. And then when we have these prolonged drying period, suction increases, going up, and it goes up to 700, 800 kPa, which is very high suction values. And then with the single rains, it dropped down to zero again. So quick saturation of the soils close to the shoulder. So these variations are significant, right? So if the soils goes these sort of suction variations, there are a lot of change in the properties of the soil. And then we have these drops with the wetting. So large suction variations occurred on the shoulder. But now when we compare it with the suction measurement on the in the center, so suction it remains very small. So no variations, no significant variation, let's say. Basically suction, so it seems that it remains almost saturated during the whole year. So during dry period as well as the wet period. So what we can discuss here now, so is that because it is sealed at the top, so during the rainfall, we shouldn't expect any water ingress from the top surface of the road, but it seems that the shoulder, that the soils on the shoulder and the drainage, they don't perform well. They are supposed to prevent the water ingress to the soil, but it seems that during the rain seasons, this water goes quickly to the shoulder and it penetrates to the center as well. So very quick ingress of water content there, and basically the suction reduces quickly. So, and at the center, when the soil is compacted after construction, there's a suction there which basically give us some strength for the soil. This basically disappears quickly after some rainfall events. So that's not good, and we should prevent it. So just to tell you what would be the outcome of these sort of structures as an example to what idea we can get from these measurements is just, so imagine on the top figure we have suction of around 100 kPa in the center and on the shoulder, and then we ideally we have to think that okay, and during the rainfall, suction should only reduce on the shoulder, and the suction and the center shouldn't be affected. So we have to keep this 100 suction there in order to keep the strength of the soil, but that wasn't the case for the site we measured. So this means that we have to revisit our design of shoulder and our drainage system in order to basically prevent water ingress from the sides of the road to the center. This is one thing to think of. But the other case is this basically suction variations of the soil on the shoulder during these drying and evaporations season. So during drying and wetting season, so during wetting it goes to zero. We can, and then during the drying, so dry period, the suction may go to 800 kPa. So, and during its service life, so these shoulder, these drainage materials, these roads materials undergo cycles of drying wetting a lot, so repeated drying wetting cycles. So basically, as Dr. Apiniti showed, so these cycles of drying wetting, the number of these cycles deteriorate the soil. It can cause changes in the shear strength, can cause changes in the permeability. It can basically affect all important properties of the soils and strength and stability of our embankment, our road embankment, railway embankment, everything. So we have to think of using a sustainable material there that remains sustainable during this drying wetting cycle, and also it can prevent the water ingress to the center of the road. So in this way, we can have a more sustainable infrastructure that can resist or that can remain sustainable against climate changing for a long period. So thanks a lot for giving me the time to talk today as well as yesterday. And I think I can pass it over to Faris now to explain their experience in Malaysia.
Thank you very much, Aras. So Faris, you should be able to share your screen now, I suppose. Faris, can you hear me?
Hello, can you hear me?
Yes, I can hear you very well. So before Faris would begin, let me just quickly introduce him. So Faris is a PhD student at National University of Malaysia, and he's working under the guidance of Professor Raihan Taha, who is one of the partner in this SEAL project. And he completed his master's degree from National University of Malaysia and bachelor degree from University of Nottingham. And he also have worked as a consultant engineer with Mega Consult. So with this very brief introduction, may I please request Faris to start your presentation?
Okay. Hello and good afternoon and good evening to everybody attending the talk today. My name is Faris Shazani Suaizan from National University of Malaysia. Like Dr. Ashutosh just said recently that I'm currently a PhD student under the supervision of Prof. Raihan Taha. And at the moment, I'm also working part-time in an engineering consulting company in the industry. I'm very honored to be granted the opportunity to share my experience. Even though among all of the panelists and speakers here, I am the least experienced by far, but I hope some of the things that I will share today will be a new knowledge to some and a reminder to others. So let us begin on the topic of the talk, which is field monitoring for unsaturated soil slope in tropical climate. So the introduction to field monitoring. What is field monitoring? Field monitoring, the definition that we're using is the ongoing systematic collection, analysis, and also the use of data that occurs during the course of a project. The purpose is to determine whether a project or a program is being implemented as designed and also having the intended result. The keyword here is implemented as designed. As engineers, we must always follow the design that was created. This is to ensure a correct and also safe outcome of the project. Monitoring is also a continuous process that occurs throughout the life of a project. You do not only take one set of data in a project, you must always monitor and analyze the data to ensure the project is going smoothly. And if there's any hiccups along the way, we need to find a solution for it and rectify it. So how do we implement the field monitoring? So first, we need to plan it out. In every plan, there is always steps needed to be followed. So what are the steps needed to be taken to implement field monitoring in a project? There are 7 steps. Number 1 is affirmation of objective. Number 2, create plan for sensors location and data collection. Number 3, purchase of sensors and instrumentation. Number 4, attend the training. Number 5, installation of sensors and instrumentation. Number 6, monitor the recordings. And also, number 7, evaluate the data required from the monitoring. Okay, so let's start at step 1, affirmation of objective. So this step is when the project is being formed. The discussion on what to do, how to do it, when to do it is all discussed here on step 1. So one of the questions that need to be answered is the duration of the project. How long should we gather the data? And also we need to set the boundaries on the project. This is due to limit the wastage. Sorry. And and you need to plan it out at the start of the project. After confirming everything, then the allocation of the resources need to be planned properly, such as time, money, and personnel. This is also the time that the plan and design need to be created. The step 2 is create a map for sensor location. So the creating a map for the sensors is a fundamental part of the planning, because the data needs to represent the whole area of the project. And by creating a map, we can see it more clearly and it can represent the data much more accurately. And then steps 3, purchase of sensors and instrumentation. The purchasing of sensor instrumentation we can reach that by knowing the site condition and the objective. And then after knowing all that, you can choose the type and numbers of sensors. Always procure or purchase the sensors and instrumentation from a reliable source, such as the one that Arash stated previously. We bought it by Meta Group and also Campbell Scientific. And by knowing the site, a better judgment can be made on choosing what type of sensors are needed. Number 4 is attend training. This is to ensure the data collection to proceed smoothly by organizing the training for the field monitoring team to attend. And through the monitoring and training, we also will learn how to install, use, and read the data obtained by the monitoring system. Step 5 is the installation of sensors and instrumentation. So we always need to follow the plan and place the sensors to be installed in their proper spot. Follow the procedure also that was taught and written on the manual, and also make sure the logger is located at a suitable place for easy access. This is to ensure that you can rectify any problem or check, make sure everything is A-OK and working properly. And step 6 is monitor the recordings. So check the readings if it's reasonable, and if you find any anomalies, rectify it as soon as possible. This is to ensure the data collection goes smoothly and accurately throughout the duration of the project. And lastly, step 7, evaluate the data. So when you're monitoring the data, after you obtain it, you need to evaluate it. So by making a graph is a good way to check the progress of the data. And when there's some abnormalities or there were some up and downs on the graph, then you have to make the reasoning to why some of the data are not showing appropriately or different than expected. So in field monitoring, you need a system to do the monitoring. This system is called the data acquisition system. It's a basic data it's a system that consists of sensors, measurements hardware, and also a computer with a programmable software. The objective of a data acquisition system is to record measurement in readable form. So you need a component to make up a system. For the data system, there is a list of instrumentation needed, which is number 1 is the data logger, which is to collect the data. Number 2 is the sensors, which convert the environment into binary data. And number 3 is the power supply, which is to power the data logger and sensors. These 3 are the main component. But to ensure a better accuracy and consistency, additional helpers or add-on are needed, such as a system enclosure, which is to protect the hardware and also the data logger. There's a cellular modem, which is to send the data to cloud system or the internet, and also a solar panel, which is to recharge the power supply or a battery. So here is the picture of the sensors and instrumentation used in our project. As you can see, there's the logger, the CR1000X by Campbell Scientific, Teros 11, is a moisture sensor, and this is the Teros 21, which is the water pressure sensor. We also have the rain gauge, which is the ECRN 100, the cellular model, the Cell 215, and also a vibrating wire piezometer, the VWP 3200. So let's start with the first equipment, which is the data logger. A data logger is typically a small but powerful piece of autonomous electronic measurement equipment. Data logger is the main part of a data acquisition system. It is similar to a mini computer. It can also be called the brain of the operation. Data loggers allow the users to capture various types of information about a specific environment or process, often gathered remotely over an extended period of time. The data logger also has an operating system built-in to help with the data collection function. And the data logger that is used in our project is the CR1000X by Campbell Scientific. So this is the component of the data logger. We can break it into 5 main components, which is the power supply, the input terminal, the power terminal for sensors, the earthing terminal for sensors, and also the output terminal, where we get the data. So the power supply, which is this, it is connected to the battery or a main power supply. This is used to power up the logger. And then this is the input terminal for the sensors. So the sensors will send the digital signal to one of this channel or terminal, and then the data logger will record it. And then the power terminal for the sensors. So there's 5 volt and also 12 volt for it. This is to power up the sensors. And then there's the earthing system for the sensors, because you need to make a earthing terminal also for the sensors. And lastly, the output terminal, which is where we obtain the data. It can be to USB storage card, or even to the like we use is a terminal model that will send to the cloud system. So how to use the data logger? First, you connect the data logger to a computer and set the time, date, and type of recordings that you want to obtain by the data logger. Step 2 is connect the sensors to the logger. Step 3, set the address of the sensors. Step 4, integrate the sensors into the logger data acquisition system. Step 5, set the number of data need to be interpreted. Step 6, set the time interval for data collection. 7 is install the sensors into the field. Step 8, collect and monitor the data regularly. So now we move on to the next component of the system, which is the sensors. So sensors, they convert the state of phenomenon to an electrical signal, like moisture, suction, right, movement. And then there's also smart sensors that have internal measurement and processing component that can output a digital value. This is mostly electronical sensors, and most of the electronical sensors is able to interface with data logger easily. So here is a list of sensors used in our project. So number 1 is the TEROS 11, the volumetric water content. Number 2 is TEROS 21, water potential measurement, or in other words, suction. The number 3 is the ECRN 100, the rain gauge. And the lastly is the VWP 3200, which is the vibrating wire piezometer. So the TEROS 11, this is the upgraded version that is now currently we use in comparison to Dr. Arash as is used in the Africa project. So it used to determine the VWC using a capacitance or a frequency domain technology. It uses a 70 megahertz frequency, which minimalizes the textural and salinity effect, making TEROS 11 accurate in most mineral soil. It also has a thermistor in the center needle to measure the temperature. This sensor can be positioned in any direction. In a vertical position, it is less restricted to water flow, and also it's integrate the soil depth much more easily. But in a horizontal position, it will provide measurement at a more discrete depth. Next is the water potential sensor, the TEROS 21. This is also the upgraded version of the one that is used just now by Dr. Arash. It's a magnetic potential sensor designed for long-term continuous field measurement. So there's he also has a ceramic for the sensors. It's measure the dielectric permittivity of a solid matrix to determine the water content of a solid matrix. The solid matrix, it refers to soil. The reference between the water content and metric potential, known as the soil moisture characteristic curve, is used to calculate the soil metric potential. This measurement approach, along with the calibration process used in the production, allows for an accurate measurement for water potential. So this is the measurement specification. So for the water potential, there is a range of -9 to -2000 kPa with a resolution of 0.1, while the VWC is a resolution of 0.1, which is about 0.1%. And the range of temperature is -40 degrees to 60. So it can be used in about almost any soil which is accessible by human. And also, it's not that big. The dimension length is about 9.6 cm and about 3.5 width of a centimeter. Oh, another thing, you always need to be aware of the range and the resolution of the data acquired from the sensors, because the range is very important to be kept in mind when reading the data. If the data acquired went past the range that is stated, then there is something wrong with the sensors. So you need to rectify it as soon as possible. So for the TEOS 11 and TEOS 21, it can be integrated using the SDI-12 protocol. The TEOS 1121 sensors require an excitation voltage of 3.6 to 15, and it also requires the sensors to have a unique address, because the factory default for SDI-12 address is 0. If you want to add more than one SDI-12 to a sensors, maybe 2, 3, 4, even 12, for ours we inserted about 24 sensors into a single logger. So we need to create 24 unique addresses of the for each of the sensors. So at the end of the sensors, there's these three main wires, which is the brown is the power, the ground, and the digital communication, which is the input or the data. So you need to insert it properly into the terminal as according. So how do we install inside? This is our site. We have two sites. I will explain later on a bit about the site. So the installation is, first we dig a hole. Make sure avoid interfering or hitting hard objects like rocks, pipe, etc. And also use an auger or trench a hole to the desired sensor depth. So when you want to dig a hole, you always need to check the site and make sure you create a plan. Check for the pipelines and everything. And for our project, the deepest the sensors were installed was 4 meters. So it was quite deep. Even by using an auger, it was a very tiresome thing to do. So, and then for number 2, we pack the sensors. So for the TEOS 11 and TEOS 21, we need to use the native soil. We need to moisten it and pack it firmly on the disc, if it's the ceramic disc for TEOS 21, and for TEOS 11, the entire sensor. And after that, we ensure the salt is properly packed, and then after we pack it, this is an example. We pack the sensors properly, and then we lower it into the trench or the hole. For deep installation, more than 30 cm, you need to pack it. For ours, it's about the shallowest was 0.5 meter, and the deepest was 4 meters. So we need to pack it properly for all the sensors. And then before you lower it into the trench or the hole, make sure you mark each of the sensors to distinguish them apart, because after you buried it, it will be a hassle to dig it out to check if you maybe mark it wrongly, or when you connect it to the logger, it shows some very weird readings. So always make sure to mark the wires of each of the sensors. So for the step 4, you connect the sensors to the logger. So plug in and then check the logger to make sure the sensor is reading properly. And verify is the reading is in the expected range, because when you dig the hole and when you bury it, it is to be expected that it's disturbed. So if you can test it by pouring some water, because it won't be very consolidated, so the water will flow much more easily at that time. So you can get some measurement. Maybe you have to be there for 15 to 1 hour to check if the reading is appropriate. And then after everything is done, you backfill the hole and tidy the wires. So you need to try to pack the salt into their natural bulk density if it's possible. And you also need to tidy the wires to avoid any accidents to occur. So the next instrumentation is the rain gauge. What is the rain gauge? Rain gauge is an instrument used to gather and measure the amount of liquid over a predefined area over a period of time. The amount of precipitation that occurs over unit area usually in millimeters, is the measurement that we are finding. So a rain gauge needs to be placed in an open field or open area without any obstruction between the funnel, which is the entrance, and with the sky where the rainfalls occur. So for our rain gauge, we use the ECR N100. It is a double spoon tipping bucket. So the internal tipping spoon makes the rain gauge more sensitive. It's like a seesaw inside it. So the water will diverge alternately to the left or to the right. So it will tip the spoon inside. The tipping bucket refers to the mechanism of the rain gauge that is used. So tipping bucket rain gauge is the most common electronic type available and is known to produce accurately and reliable result. So how does it work? So when it's raining, the water falls into the funnel located at the top of the rain gauge. And the funnel will direct the water into the top of the 2 tipping buckets. The tipping bucket will have a water limit defined by the manufacturer operator. And once the water collected reaches the predefined limit, the bucket will tip and hit the calibration screw. As this happens, the second bucket is lifted and start to fill. This process of filling and tipping will continue as it rains. And the bucket will pivot and hit the calibration, and the switch is activated. Then the rain information will be recorded electronically. Okay, so how do we install the rain gauge? So first, we mount the rain gauge on the mounting bolt at the desired height. Secure the rain gauge to the pole, ensure that it's level. There's always a bubble. As you can see, there's a bubble here. So make sure the bubble is correctly level. And then plug the sensor into the data logger and use the data logger to apply the appropriate setting to the sensor, and then gather and secure the cables to the mounting pole. So as the ECRN, the resolution is 1 tip per collection, and 1 tip is about 0.2 millimeters. So the next instrumentation is the piezometer. So the piezometer is used to measure the pore water pressure in the soil, earth rock field foundation, and also it can also check the concrete structures. The pore water pressure is used to detect the level and flow pattern of groundwater. We use the vibrating wire piezometer. It finds its application in the measurement of positive and negative pore pressure in the soil. Okay. There is all the sensors. Now we go to the rechargeable battery. So what is a battery? Battery is a device that converts chemical energy into active material, which is directly into electric energy. Rechargeable battery needs a converter to convert the power from a solar panel, and you use a DC to DC converter to maximize the energy harvest from the solar panel or the photovoltaic system to help regulate the amount of DC energy running to the system. So this is a solar panel that we use. It's an assembly. What is a solar panel? It's an assembly of photovoltaic cell mounted in a framework. It uses sunlight as a source of energy to generate direct current electricity. And solar panel is quite efficient, but it's typically in 20% range of conversion, but it will greatly be reduced by the dust, ground pollen, or any particulates if it's started to accumulate on the solar panels. So it needs to be cleaned regularly. So that is on the first site we install the solar panel. It's quite high to make sure that nobody can vandalize or steal it, and also it can obtain the sunlight much more easily. Okay, the next one is the cellular model, the Cell 215. It works by connecting to the internet network with the help of the SIM card, which is a subscriber identity module card, the one that we use on the iPhone, on the phone, on the Android, and everything. It can be also be connected using the Ethernet. Cellular is a term widely used for 2G, 3G, and 4G network. This device can be mounted on a wall or on the pole. A public static IP address can be used, but it is much more better if we use a private dynamic IP address to ensure that it be much more secure and less vulnerable to unsaturated traffic, so other people cannot disturb the traffic flow of the data. And lastly, the system enclosure is a cabinet for electrical or electronic equipment to mount on. So this is the system enclosure for our site. The function is to prevent electrical shock to the equipment user, because the electrical discharge will be grounded by the copper plate, and also to protect the contents from the environment, so they won't be harmed by the weather and the climate. So this is the first site, which is the Bukit Mewah. So it's an open hill with 3 berms and residential area both at the top and the bottom of the slope. There is no big trees in the vicinity, but there's some vegetation around. So it's quite high. So as you can see, we obtained the site around 25th of February 2020. It was very clear and everything. It's the site is quite big, so we just make use of the middle part. So we inserted, this is the top and this is the bottom part. So we inserted the instrument at the top, the middle, the crest, the top, the middle part, and then the toe, or at the bottom of the slope. So this is the dimension of the Bukit Mewah, or the hill. It's about 6 meters for the first slope, and then it's about 4 meters at the bottom slope. So it's like a 2-3 berm. Access, because the sensor wire is not long enough, we need to put the enclosure in the middle, so it can be accessed by both the lower of the sensors and the top of sensors. If not, we need to buy 2 loggers. So we inserted in the middle. To access the site, we need to use a rope because it's quite steep. As you can see, there's rope every time we want to access the site. So this is the 3rd March. This is when we started to begin and to install the instrumentation. So we start with the auger, we dig the hole, and we pack the soil. We also did a borehole to get the SI of the SI to check of the soil characteristic. This is after we finish planting everything on the 7th of March, and it's we pack it nicely, we close it, and then this is for the piezometer. So that's the first site. This is the second site, which is a partially shaded hill with 2 berms. It's also the same. There's residential area both at the top and the bottom of the slope, but this site has a lot of big trees with canopies. So it's a bit different than the first site. So as you can see, the site is quite close. This is the first, the toe, the middle part is here, and then the top part is quite high. And there's a lot of trees around here. And this is the dimension of the site. It's not as high as the first one. The first one is like about twice as high. So we started with SI drilling and to get the data, and after the installation, this is how it looks like. So you can see some of the wires we cover it with protection, and also sometimes we also use the PVC to make sure animals don't bite it off. So this the kajang utama. This is solar panel. As you can see, we installed the solar panel quite high. This is about 2 meters high, because the area is full of canopies. So to ensure that we collect good sunlight, we install it quite far from the actual site, and we need to manufacture our own pole. As you can see, we make sure it's tidy and nice. So this is an example of the data we collected this is for Bukit Mewah, the first site. As you can see, this is for the suction for Teros 21. So there's 1, 2, 3, 4, 5, this is about 12 suction on the first site, and they show all the different readings. So from this reading, you have to rectify if there's any problem, like why is this suction, the BD is 100, and why is this 170? And all of this needs to be checked and needs to be assessed by making a graph. You can easily see the data, and also is it showing a proper result. So this is one of the example that I picked, is a data from 18th of July. There was a slide of rainfall, so we can see that there's the rainfall, the rain. So this is the wetting period, and then this is the drying period, and then there's the wetting period again, and then there's drying period again. So we can check from the graph, if we implement the graph, so we can see the rainfall, and then how does the sensor react to the rainfall. So you can see the sensors react to the rainfall. From there, you can deduce that the sensors are acting as intended. After the drying period, it went down. Some of it still slowly went down. This is all due to the localized effect. You can also use it for the suction. For the suction, when there's rainfall, the suction goes nearer to 0. Yes, and then when it's during the drying period, it's slowly going down. So I want to share some of the issues and problems that occurs during the site field monitoring. So I separate it into major problems and also minor problems. So the major problem is the COVID-19, rapid growth of vegetation, lightning strike, and infestation of termites. For minor problem is low power in battery and also vandalism. So let's start with 19. So we acquired the site during the February 2020, and there was during the starting of the COVID. So in Malaysia, we just received the first order for the movement control order, the quarantine order on the March, and that's why we only have like about 5 days of installation. And then what else? The COVID-19 also delayed the data system implemented, delayed the testing for the soil affected, delayed the data gathering, difficulty to access the site, and also it's difficult to meet and discuss the issues of the field monitoring. So about the COVID-19, when we extracted the data, we extracted in undisturbed sample, but due to the COVID, most of the technician and the lab assistant were unable to go to the site, to the site and also to the lab. So we have to store the undisturbed sample properly for about 3 months until they are able to use the lab again. So the data we obtained was quite inaccurate from the SI. And then for the data system we implement, we have only 5 days, so we weren't able to check if it's is the data is appropriate, or the data is okay, or the data is reasonable. So when we arrive back, it's quite difficult to check it due to the COVID limitation. We are unable to move around as much. And the next issue is the rapid growth of vegetation. It make it very hard to access the site. The readings from the sensor were disturbed. The reading from the rain gauge were disturbed. So this is the first site, the Bukit Mewah. So as you can see, the vegetation has piled up. Due to the COVID-19, we were unable to go to the site. So the vegetation piled up so very quickly. This is when we were starting it. Everything is quite clear. There was no much of a vegetation. And during the 9 April, when we were allowed to just go and check, it's quite hard to see because everything is already very, very thick and a lot of vegetation. So then only the next day I was able to go after we cleared a path towards the system. Right. So yes, the vegetation grew very fast at the site. And this is on the 5th of May. We still need to do some clearing. We've been constantly clearing, but there was still a lot of vegetation and it's still quite thick. And yes, in comparison to when we just obtained the site, it's for a month, it's very, very fast. And this is on the 25th of August. We went back because there was another wave of COVID. So we need to be quarantined again. And we can't find the entrance to the site anymore. The vegetation already piled up so very quickly. This is the, you can see, I just went down. It was quite slippery, but yeah, the vegetation is very thick. So how do we maintain it? We at first we use salt and dish soap to clear, but it didn't work. We used vinegar. It also didn't work. We used weed killer. It worked for a while, but after that, the vegetation is too strong. It just go back. So our maintenance now is just every time before we go, a day before, we just clear the site. Another major issue is the lightning strike. So lightning strike happens during thunderstorm, and in Malaysia, we have a very heavy thunderstorm. The thunder overloads, the lightning overloads the wire and sensor. Some of the wire sensors also was burned out. So this is some of the example of lightning strike. Most of it is burned out to crisp. I didn't save the burn part of it, and it's very difficult. It was a very difficult procedure because we weren't sure what happened. We just noticed that suddenly there was thunderstorm. The next day, everything went out. So as a prevention, we installed a lightning surge protection system. And how it works is it intercept and redirect the lightning surge into the earth. This is also called earthing or grounding. So the lightning protection system includes lightning rod, conductors, and ground electrodes. Another major issue is termites. The termites bite the wire's casing. It doesn't bite the wire, but it bites the wire casing. But when they were biting the wire casing, they also bite the wires. So when the wires is exposed, it slowly rusts and it slowly became unable to be used. So this is some of the example that of the sensors that was bitten by the termites. There was like multiple sensors, and we need to buy more to change the sensors. It was quite a hassle because we need to dig it up and remove the termites. So one of the way that we did was we put some of termite bait around the area and pour some vinegar also around the area. For physical, we tape and seal the plastic casing to avoid being bitten. At the moment, it has not failed yet, but hopefully it will maintain that way. So for the minor issue is prolonged cloudy days. As you know, we use solar panel to to generate the electricity. So when the solar panel cannot receive sunlight, the battery was unable to recharge and the power slowly dwindled down. And this affects the reading as the battery slowly dwindled down, it is not able to power up the logger and also the sensors. So slowly the reading of the sensors will go haywire and also show inaccurate result. So one way to mitigate this is having a spare battery to recharge when the battery went down a certain threshold of voltage. Another thing is vandalism. There were slight cases of vandalism, like people throwing drinking glasses, and also some of them tried even to dig out our sensors. There was sign of it, but they were unable to reach far because it was 0.5 meters was the shallowest. So I think they give up halfway. And also, so how we mitigate it is we install lock and cages for the enclosure, and also we bury most of the wire to avoid them from finding the location of our sensors. So that's all for me, and the conclusion I can produce is always follow the plan and design of the project. Always monitor and analyze the data acquired from the field monitoring, and also identify possible issues early and set preventive measures. And the most important is safety is the #1 priority in any aspect of the project. Thank you very much for listening. That is all for me.
Thank you very much, Faris, and for the wonderful presentation and highlighting the basics of instrumentations and what are the challenges ahead of us when we try to instrument. So it was wonderful listening, definitely. And also I'm thankful to Aras as well. For the second consecutive day he has spoken, and he gave a wonderful idea that like how we can instrument the transportation infrastructure, and that would give us an important aspect on the result, and that would suggest that what should be the design methodology, how the water content within the subgrade soil is changing. So it was wonderful listening to you as well. So we don't have time now to take the question. So of course, those who are having questions, they can directly contact and message to to both Aras and Faris. So we again thank you for your contribution, and now we will move to the next presentation. So the next presentation would be given by my colleague, Dr. Uday Kala, so who would be speaking on multi-scale approaches for landslide monitoring. And so before he would start, I would request Aditi to kindly introduce our speaker.
Thank you, Dr. Arash and Mr. Faris, for the wonderful presentation. Now, I would like to welcome and introduce Dr. K.V. Uday. Dr. K.V. Uday is currently an assistant professor at IIT Mandi. He completed his PhD from IIT Bombay. He has 13 plus years of experience with 2 years in industry, 3 years in research, and 8 plus years in academics. He is one of the pioneer faculty of civil engineering at IIT Mandi. His research areas include landslide disaster risk reduction, nature-based mitigation solutions, biogeotechniques, and machine learning in geotechniques. He is the author of 20 plus research articles, 30 plus conferences, 2 granted and 4 filed patents, and received a research grant worth rupees 3.8 crores. He is also the founding director and part-time CEO of startup Intest Services Private Limited, which is incubated by IIT Mandi Catalyst and supplies the developed landslide monitoring technology on a commercial scale. I welcome you, sir, and thank you for your valuable time.
Yeah, thank you very much, Aditi, and a special thanks to Ashutosh and the organizers of this particular course for inviting me for this particular presentation. Again, probably just after Faris, I will be the next probable low experienced person who is talking on these topics when you're especially on this landscape monitoring. And a special thanks to again all the speakers, starting from yesterday's first presentation by Professor David to Professor DN Singh to the end, and today most importantly the opening talk by Professor Apiniti, and followed by, of course, Faris, who has given us a wonderful idea about the monitoring. What is the scheme of monitoring? What are the various methods, or what are the various options we have while monitoring? And especially, I think they have gone wonderfully into the topics of suction and slope stability related things, which probably will be missing in my presentation when I'm making. So definitely, when I'm moving ahead, I know where I need to put my feet depending on the presentations which we have gone through today. So I'm attending this course as panelist as well as probably as an expert speaker, but still I'm sure there is much of things which I learned in the last 2 days. I hope the same is happening with all the other participants. So quickly, without taking much time, I'll just go through this particular presentation on multi-scale approaches for landscape monitoring. This is what of a minimum experience which we had at IIT Mandi in last around 5 to 6 years. When we go into the presentation, you will understand what is the need of us to talk more about this particular approaches for landscape monitoring, and especially thanks to all the funding agencies who have been supporting us very consistently in order to improve the current conditions at this area of Himachal Pradesh. So when I'm going to the presentation, we are going to talk a little about landscapes, of course, what is the need of monitoring, then what is the approach we need to take up, and different scales when we are looking into regional scale, zonal scale, local scale, and site specific, when should we go for each of these particular case will be the main focus of the presentation. Of course, again, thanks to Faris, he has already covered a lot part of instrumentation. I'm going to slightly differ from the other presentations in the instrumentation, where I'll be talking about a surface level monitoring system which we are taking at which we have developed at IIT Mandi. And definitely when we are doing all this, we are now on a verge of looking into the modern technologies, including machine learning. I'll be giving a little idea about machine learning and how this machine learning can be useful for going for predictive analysis, and thereby how the disasters can be either stopped or can be dated, or can we understand the happening of a disaster much before time, so that the risk management options can be looking for. And to start the presentation, yesterday my colleague has already talked from IIT Mandi, but I thought I'll take this option of introducing you to the campus of IIT Mandi. Well, we are much between the beautiful valleys, as you can see in this. A specialty about our particular campus is we have two campuses, one in the south and one in the north, which are aerial distance is 1 kilometer or 1.2 kilometers typically. But when you have to travel between the two campuses, you are traveling 5 kilometers because of the path, again, which we probably define as tortuosity in geotechnical engineering. The same happens in hills and valleys, as all of us know. And yes, we are very near to snow peaks and snow and beautiful valleys. And as also there is a good river, a perennial river, which is cutting across the campuses, both the campuses. So we are good with all the natural conditions, and this, which I say, is a bird view. But however, we as a geotechnical engineer, when we start running into the cutting down the scale, then we see, should I say, textbook definitions of slope failures, which includes a block failure which is coming in the rock, then of course a slide which has happened. Then when you look into the material and of course the surface floors, morning I think both Dr. Apiniti as well as Dr. Arish was talking about the surface flows which keeps on happening on typical locations. As of course we are also into those particular areas where we have only surface flow, hardly it's not even half a meter to say. And wonderfully, as again discussed by Apiniti, we can clearly close or we can avoid these particular problems by going for bioengineering in these particular locations, which is again another focus in IIT Mandi which we are trying to do. And the second thing, you can look into the to the material which is falling in the slope, which contains of a very exactly soil. Sometimes it's all rubbles and cobbles and boulders which are coming in, and sometimes, yes, again you can see a very good gradation of the soil, which can be soft soil to fine grained to coarse grained soils which come in. So when we are looking into these particular aspects, I think just to tell you, all these images are collected between the travel which you take in from the district of Mandi to the campus of IIT Mandi, which is like 19 kilometers or say 20 kilometers. And we have in the last 6 years mapped around 82 landslides happening in this particular area of 20 kilometers. So you can see, sorry, so 56 landslides which has happened in between 20 kilometers. So typically more than 2 per kilometer, you will be able to see such slides which are small to comparatively very large. So when we are talking about all this is a point at which we define the landslide as a moving from the slope. This is very important definition which we have taken up for understanding the monitoring aspects. Next, the most important thing which we need to look in is the disaster. Landslide is a disaster because it claims lives, especially in hilly terrains and most of these particular areas. And of course, this also includes a lot of infrastructure loss as well as financial losses which keeps on occurring. And most important thing, this is spread over huge areas. You know, we're talking about 500,000 kilometers square. So we can see it's not that we are having a particular site or a particular point at which we have to probably monitor or probably look into the requirements of monitoring. So that's where I have taken up this particular presentation on to see what type of monitoring system should we take up when we are talking about different scale of areas or different zones of areas. And apart from this, surely it is worth mentioning that after a good amount of research as well as applications in the field, there are more than 72 plus perfectly audited structure mitigation measures which are used for mitigating landslides. So when you're talking about the various aspects of mitigating the landslides, then yes, I need to show you a particular case study of Kotropi, which is hardly 50 kilometers away from our campus of IIT Mandi. As you can see, the Magnus point of it, you can see the small location or the small hutment which has missed the debris flow. You know, you could see if the same debris flow would have gone through this already, this has claimed about 46 lives. If at all the debris would have gone in a different direction, things would have been totally different, or the numbers would have been totally unmatched, because more than 300 people are living in this particular locality, which you can see in this particular image. So now the case comes in. Yes, we are talking about a landslide which is 250 meters high and 150 meters on the width. When it closed away a road which is running exactly, or a road which was running exactly here, and it has claimed 46 lives because again this happening in the midst of the night, whereas in the mornings only more of the people are very much trained to this, that they can see the soil movements happening on the slopes and the disaster could have averted. However, this happening in the mid of the night at almost like 2 a.m. in the morning, this has created the problem, and the amount of debris again you can see is so huge. Now if I ask anyone to go for what type of structural measure you want to go in for this particular activity, then probably the answer will be difficult. So that's where is the requirement where we talk about the need of monitoring on such slopes. And again if you are seeing only this particular part, then I am always worried about this part, because I'm not very sure which part of this is going to come down, and if at all if it is coming down, again there is a major life loss associated with this. So this was critically in our mind when we started working on this particular area. When we go into the literature, when we look into the areas which are subjected to landslide, with of course a very limited data which we had, I'm just trying to show you these are the areas across the world which are facing this particular issue. Of course, we have been hearing from the speakers from yesterday that Asia is a major part, and the western part of Asia is again a major is affected heavily by these particular regions. And now I'll focus into that Himalayan terrain where these particular landslides are happening in a very projected way, where you can see that the events are distributed from being very sparse to very big, very huge. The same Kotropi landslide which I just showed you, which happened in 2019. Most important again, when we look into one is the loss, one is the financial loss, and the other, which is not acceptable probably, is the life loss associated with this particular slides. So looking into this, we started this idea of monitoring, and when we started looking into the monitoring, we have various approaches starting from structural measures, which we discussed. 72 type of structural measures are already existing, and of course that doesn't make a major point of this particular presentation. So whereas I want to talk about non-structural measures or non-structural options of which we look into these particular areas. And when we look into the non-structural measures, we are mostly talking about monitoring and early warning. Again, thanks to Abhiniti and Farhan as well as Aris for giving us a very good idea on how this monitoring is taken care of and how we release early warnings based on various thresholds for different conditions which have been shown from the morning presentations. I'm going to little go on the same, where most of the topics we're talking were on the field scale monitoring. I am trying to get onto the particular scale where I'll be talking about a local scale monitoring, then zonal, and lastly regional. Or we'll start probably from regional and we'll try to move towards site-specific monitoring to the end of the presentation. And when I'm talking about these particular scales, don't take it typically like a geologist or maybe the remote sensing guys who talks about having 1:50,000, 1:5,000, 1:7,000, or 1:10,000 scales. For me, in a simple word, there are many specific points or very site-specific points within a particular locality or which comes into a local scale. Many of such local locals make a zonal scale, and many of such zones combine to become a regional scale. So it depends on what type of data you are having, and accordingly we'll be able to cut the requirements into which scale we need to measure or which scale we need to look into monitoring of this particular science. So now first we start with the regional threshold. For me, the regional threshold, of course, above this is always the satellite imaging, which can be done at a much higher scale. But at least for me, I am just defining it as regional scale. So for me, the regional scale is is rainfall based. Of course, whatever I'm going to discuss in this particular presentation are majorly or to the best of the conditions. They are all rainfall induced landslides, and based on when we say the triggering factor itself is rainfall, then that probably, as per the researchers, that is the best way you can cut down or you can look into the thresholding aspects of this particular at the regional scale by using simple rainfall. So for this, we have been looking into literature, and there have been a lot of data which has been published. Especially, again, I'm focusing only on the Indian Himalayan terrain, where there are huge number of intensity duration graphs which are given, which gives you an idea about the thresholding which needs to be given for a given particular landslide of when can we expect a particular landslide. I think there were questions also from the audience in the last few sessions, again answered by David Toll, that when the duration, when the intensities are small, and if you're expecting landslides, that is absolutely possible because probably the rainfall duration has been a longer duration. So it's both intensity and duration, both of it, which plays a major role of it. When the duration is high and a lower intensity can easily create a condition of slope failure. So for this, of course, when you want to do this, what you need to have is a data, or what you need to have is data, which is rainfall data. In this rainfall data, again, it is suggested or it is preferred to have a data which is varying from time to time. Whereas when you are seeing the gray color gray color box chart, this is mostly the data which is coming from 30 years. Whereas the yellow is the one which is coming from last 5 years. So you can see there is a huge difference in the intensities of the data, which is intensities of rainfall which is received in the particular region. And that is where, again, I could see from a different projection altogether that the landslide intensities have increased in this particular area, and we need to cut it down. So we have started working on it, and now we have developed our own intensity duration chart with which we will be able to probably look into the options of thresholding or giving an alert to the whole district saying that, okay, this is the rainfall which is happening, and if this is the intensity and the durations which are going on, if you are doing by using a simple rain gauge or related aspects, again as showed by Faris during his presentation, it should be good to threshold or to give a warning based on this particular intensity duration chart for a regional specific. I'm talking about a regional specific point at this particular point. And there was yet another question in the chat box, as I can see, that, okay, if you want to, when I'm saying, I'm talking about a region which is coming to almost 30 days because of the availability of the data. However, 30 days may not be a right time or right intensity. 30 days may not be a right time or right point at which we can be able to monitor or measure this particular data. So that is why we always talk about antecedent rainfall incidents. And if you want to check how do you want to take antecedent rainfall incidents is antecedent rainfall time, then you need to collect a lot of data on what rainfall has triggered, how many landslides in that particular location, according to which you need to just put a relationship between that between different days of cumulative day rainfall and the daily rainfall scale. Again, in the morning we have heard from, if I'm not wrong, Apiniti, that in that particular area it is 3 days of rainfall, which is giving 3 days antecedent rainfall is giving them a good threshold. However, that is not at all a case for at least Himalayan region. As you can see it clearly, in 3-day rainfall, our probability or our effect is only is down by 21%. So that is why we started moving much into the for further scales. However, just for the projection, I'm just showing you 3, 5, 10, and 16. However, we have worked out for each and every day on how each and every day's cumulative rainfall can be a good identification. So we found finally at 16th day, we are able to see that now the rainfall, the landslide incidents no more depend on the daily rainfall, but they mostly depend on the cumulative day rainfall. So that is why we are able to see that our particular region in Himalayan region at least needs 16 days of cumulative rainfall to look into the aspects of thresholding them with respect to rainfall intensities. Not needed with 30 days, now it is only 16 days, and further in the presentation we'll talk about how probably we can reduce this further. So this is all about the it's the same 16 days we are talking about, and this is how we are looking at regional threshold. Now when I bring it to the zonal threshold, as per again the literature, most of the literature talks about zonal threshold being data driven. So we need to have a lot of data in order to get into zonal threshold level work. So it was otherwise probably somewhere between medium difficulty to difficult, where we talk about this done in the remote sensing or by using geological data from the data which is mostly available, where most of the information is available from the satellite or mostly from the GIS related information. However, when it comes to expert in geotechnical engineering, then it becomes very difficult. So we have taken up this particular opportunity where the same road which I was speculating from the starting, that is from the district center to the IIT Mandi campus, we have this 20-kilometer road which is coming. And what I try to do is I find my students, and they have collected samples from all these particular locations, which contains of mostly we have focused ourselves only on soil. So at this particular time we could collect 82 locations. We could get different samples. They are both undisturbed, disturbed, depending on the terrain and the available conditions. And accordingly, we have tried to characterize all these particular soils first based on the geological characterization, and next on the geotechnical properties. So we were just starting. We had no idea how to move ahead in this particular topic. So we simply have performed all the possible geotechnical characterization tests in order to understand what is the characterization or what is the type of soil we are encountering in our day-to-day activities, especially in this particular area of traveling from the district center to the campus of IIT Mandi. So we collected all the information. Apart from this, we also had some data collected from field investigations, which include the moisture content, elevation, field slope, again, which happens to be major factors to indicate. So to the end of this particular analysis, we could see that we have 22 parameters from each of the location, where we have collected 82 samples or 82 locations from which we collected the soils, and 22 parameters was taken out. And after the time, we could understand out of these 82 locations, 58 were landslide or 58 were the locations where the landslide happened, and 24 were the locations where there was no landslide. So now when we are going for a simple statistical analysis, we were unable to see any working model. So that's why we quickly went into machine learning algorithms so that the computational efforts can be reduced. And of course, machine learning gives us a very good idea on specific problems related to, again, slope stability analysis. That's what we are also understood from the literature. So looking at it, we quickly formulated a particular model by which we'll be taking up the options. There are two most important things which we wanted to take out. One is the feature selection method, by which we will be able to identify what are the contributing factors, and based on the contributing factors, can we go for zonal level thresholding, saying that, okay, if this is the level of, or if the angle of friction of this particular area is less than this, can we say this area is more prone to landslide, or if the permeability is more than this, can we go for thresholding by this particular algorithm. So we worked on a quick, what we call is a UROC, that is a recipient of operating curves, which gives us the accuracy of the models which we worked on. And again, we worked on different machine learning models in order to understand the same options, to the end of which we could rank typically on what scale, or we can say at a particular correlation coefficient we could get on which parameter is contributing higher to the landslides or to the slope instability which is happening in this particular location. As you can see, the list has all 22 parameters. And to the end of this particular exercise, we also have looked into what are the various combinations of these particular parameters which are giving us a best option of identifying the susceptibility of this particular to identify the susceptibility of the landslide in this particular location, where again we say that a typical combination which has come out with 6 parameters, that is relative compaction, slope angle, porosity, moisture content, then saturated permeability and the internal friction angle, giving us the best of the combination which can be used to formulate the which is used to zonate or identify the zones which are probably subjected to failures. So based on this, we have come out with a point that, or we have come out with a conclusion saying that while these particular parameters, the slope angle, internal friction, permeability, and compaction are relatively constant at a particular location. Yesterday again we had a very good discussion on whether these parameters will be constant or consistent across the time with the presentations which we had yesterday from Samprada as well as Professor Singh. Both of them have given us a slight idea on how the parameters change with respect to time. So we have confirmed that these particular parameters are to confirm the location of the sensors, and the field moisture content, which keeps on changing or which changes because of the triggering factor of rainfall, can be a parameter of monitoring. So based on this, we have devised our own method of monitoring at the field, which I will be discussing slightly later. But to this particular point, as you can understand, first I had the various data of rainfall. Second, I have a very good idea about the geology in this particular area. And third, I have already characterized the parameters in the soil based on the geotechnical characterization I have done in the soil. So now, as I see in rainfall, I could get a maximum of 16 days cumulative rainfall. Whereas by using geotechnical and geological, just now in the last slide, if you have noted, then I'm getting an accuracy of 0.958, which is definitely not a very good working option, at least when you're using a option like machine learning. So we wanted to go further. We want to see what is the combination which brings in the best outcome of this. So in the meantime, we already started working on the various values of AEV, that is the air entry values, which becomes again the cause or which can give us a very good idea about the unsaturated profile on this particular soil and whether it has any role to play. And again, it was discussed that IIT Mandi is very new. We have just started our civil engineering department from 2015, so hardly 7 years from the start. So we are still in the stage of setting up a lot of equipment and requirements. So we'll be soon pacing up again with the world-class facilities with these particular opportunities we have. So in the meantime, as just now we discussed, the various data we had on rainfall, geology, and geotechnical, we started to club these particular parameters to understand how this can be done. Of course, the same machine learning, which is another statistical method, which says that 16 days is the time which I need to have to find a consistent model which is working to predict the rainfall. Again, it is 95.5% accuracy. Now, when we talk about adding a morphological parameter, that is a site-specific parameter, I could reduce the time from 17 days or 16 days to 13 days. So at the 13th day, I could see that now the model is working well with a reasonable accuracy. Again, a little increase in accuracy, but I could reduce the antecedent rainfall periods or antecedent rainfall time which we require. And further, when we have added the geotechnical information or geotechnical characterization, then we could see that the prediction has now gone really well. 100, of course, should not mean exactly 100%, but yes, we are able to predict based on the simple training and testing 30 and 70. We could easily understand that it improved the accuracy of prediction, and still the antecedent rainfall remains for 13 days. We need to definitely have. And then further adding all the 3 parameters, rainfall, morphological, as well as geotechnical engineering, geotechnical parameters, we could reduce again by 2 more days. So we are now able to get it at 11th day, again maintaining the same level of accuracy, which is very near to 100. So by which we can understand that probably by using a good statistical model, especially machine learning, by using huge amount of data which we are having, we are able to again go into a line where we are able to threshold, or we will be able to predict which of this particular place or where of this will be the landslide should be happening. Now we are in the case of validation. So probably after this particular year, we should be able to submit this particular paper to the journal, which is freshly cooked for now. Now I'm getting back into the monitoring system, which will be the last part of my presentation, where in the earlier slides I have showed you that we have identified the points at which the location or where we can locate the landslide, and we also come into a location where water content is, or water moisture content is one of the major heating parameters also in this particular area.
again, in line with whatever presentations we have been hearing from yesterday, moisture content is the single factor which represents or which gives you a very good idea about the slope profile or the condition of the slope before failure. So when we look into the literature, of course, we have a lot of existing techniques or existing methods by which you will be able to do. Till now, we were mostly looking into the part of conventional geotechnical landslides by using various sensors, including TDR, FDR, and we also discussed on piezometers, installing piezometers to get very good idea on this. But however, when I was looking into these particular options, it becomes very difficult to handle so much of data, especially in this particular location. And majorly when we look into, again, we are talking about a major aspect, which is cost, where when I say that when I want to go for such a huge monitoring, especially in the areas, it becomes very costly. So we wanted to bring this cost much down with the existing technology or whatever we are having currently by using simple MEMS-based sensors. So looking at it, we developed our own system. First, the archaeology is very simple, where we are again thanks to Faris on this particular point that he has cleared most of the parts which I need not probably cover here. Where to say yes, we are having our monitoring systems, they are into place, and we are putting all the information into web servers by using the same GSM analogy. And at the cloud itself, we are able to fix up the threshold algorithms, which are seeing how the data is changing, and whenever the data is crossing the threshold, we are rechecking the values, and accordingly we are releasing the signals, where the alerts can be done either by mobile alert or on web-based servers, wherever the information is available online for public. And very similar to probably what Faris has showed us just before this presentation, our monitoring station looks something like this. This is the solar panel which powers our whole set, and then this is the tipping bucket rain gauge, again the same whatever has been discussed. And lastly, our set of monitoring system is slightly different from whatever has been done, which I'll try to go further. But yes, our the PCB is located in this particular box, and you can see the wires which are going on, which are the sensor nodes which are going into the soil. So for now, initially when we started, we never wanted to one is of course the financial crunch, and the second definitely we should talk about the field aspects, where in this particular soil it becomes very difficult for drilling and going deep into the systems. So we wanted to develop a system which is mostly surface based. So we have taken up these particular sensors, which include the MPU6050, which is typical accelerometer sensor, which we have in our smartphones, all of us, and we use the same smartphones for checking the tilting accuracies, etc. in various applications. So we have taken up the same sensor. Apart from this, of course, that rain gauge has been very well explained by Faris as just before the presentation. The same tipping bucket which he was saying, that whenever the water is filled, then it tips down, whereas the next tip comes into picture whenever this is filled. Again, we are able to see, we will count the number of TikToks, and we are able to see how much of ml of water has run through this particular from this particular line, and thereby what is the intensity of rainfall which we have measured for that particular time. All of this is digital, so all the information is gone into the cloud. Next, we have temperature humidity sensor. We wanted to see how the after effects of the rainfall or before effect of rainfall, what is the temperature, how the humidity are changing, and accordingly does it show any influence on landslides. This is one more thing which is important. Apart from this, we are also putting up a ambient light sensor, because we want to understand the aspect of the landslide, where the slope is towards the sunshine, or whether the slope is towards the leeward, and how this particular light intensity is changing with respect to time is another parameter which we thought that should be interesting. Then of course the capacitive soil moisture sensor, where I'll be able to get the volumetric moisture content, and accordingly depending on the site locations I can convert it into gravimetric moisture content, and sometimes it's good sometimes also to go into volumetric moisture contents. And lastly, we also used force sensor to check if there is any local changes or local disparity, and all this particular information we are able to send it by using simple GSM cloud and the same landslide setup which I have shown you probably before this particular setup. And of course we are also using a barometric pressure sensor in order to see or predict the rainfall happening before the time. So these are the ranges of the sensors which we are using in our domain. And typically when we started this particular location, we have identified, luckily again being in the campus of IIT Mandi, the slopes are hardly few feet away from our location. So we have taken a particular location which is prone to landslide. We have identified a tension crack and we have put all our sensors and started maintaining data. Again, the data looks more or less the same what Faris has showed, except for the point that he was more into looking the suction aspects of the soil. However, we were more on capturing the accelerations or movements which are happening at a particular location. So we captured the temperature, humidity, pressure, rainfall, light intensity, soil movement, force and soil moisture at a particular location, and we are able to gauge the data with respect to time. And when we are looking into the accelerations, we are having point accelerations which are at a base of 1 microsecond. So thereby, by using simple kinematic equation, we are able to calculate the displacement at that particular point and integrate it with respect to the time in order to get the same displacement across the location of time. Probably this can be a small help for you, Faris, when you're talking about the problem of having the data, having the issues with the power. Probably if you can reduce the amount of data which you are capturing by using again some statistical methods or something, you can definitely cut down on the power requirements of your sensor. The sensor can sleep for probably, for example, our sensor sleep for 9 minutes, wakes up the 10th minute, and it collects the data. Again it goes back to sleep in the next 1 minute. So typically in 10 minutes I'm getting one reading, and that particular one reading I'm assuming to be the same across the point. However, you can also put a small note in your coding saying that, okay, if at all there is any abnormal changes which are happening in your sensing values, then the sensor is open for the whole 10 minutes and is sending you the data whenever it is at the crux of the location. This can save a lot of your power, and of course you are already with the backup of your battery and all, so for the next probably stations you can probably use it. So we are using the same concept where we keep on getting the data and we keep on accumulating by simply using the z-score concept. And you can see one particular case study which we had in Nainital, which is in India, again in the Himalayan region, where we have been aggregating small movements over the time, and slowly after a particular time the small movements integrate to become a moderate movement. So this is the time at which we are saying, okay, there is a threshold which says that there is a breach of the number, and thereby we start improving or increasing the requirement or increasing the focus of the movement. So earlier small movements, normally we don't keep it much into focus. The moment it is converted to moderate, then it, of course this area will be under now consistent evaluation. So apart from this, we also have a warning system right away on the roads. Currently we are not going into locality or residential scale. We are only keeping it on the road scale because there is a good chance of errors, as again rightly pointed out by Faris in his presentation, that there are good amount of false alerts which can come out in your particular from your particular monitoring station. So that is why we are only monitoring on the road, so that we can stop the traffic for 10 minutes, don't mind wasting their time instead of losing their lives. So that's what we try to communicate, and we have been collecting all the information, and according to the data which we are collecting, we are able to give the rainfall alert as well as the movement alert if at all something is happening on the site directly to the stakeholders or the administration. And then in a particular situation in Mandi, in the same area where earlier in 2017 I showed you in the starting, where 46 lives were lost, the district administration wanted us to keep our sensor there and start working on. So we could keep our sensor and when we started collecting data somewhere in 2018, when there was again a minor flood, a flash flood which happened in that particular location, which has triggered one more landslide because of the sensors which are present on the at the point. We could avert a major disaster which has happened, and it has been covered in the news, as well as the articulate which has been given by the district administration, whom you can see in the picture here. So he has given he has confirmed that the sensors have given them a good information, and it could help them save lives much ahead of time. So thankfully the sensors worked, and of course we have taken care of all the situations in the site, and we averted most of the disasters. And then of course in no time it has gone across most of the publications and in most of the news articles. And finally, after all this, we have got good amount of funds. Now the situation is slightly different. Now we are able to put a lot of monitoring stations in our particular location. Again, we are still in the level of data accumulation, data collection. So now from this particular information, we are able to collect which areas are now subjected to or which are prone to soil movements. So once we understand there is any typical area, if we can find out, then probably I will be now interested to go to that particular site and start working on this particular area of soil suction. So give me 2 years probably, after which if I'm able to present again to the same audience, I will be presenting you more details on the soil characterization, suction, and the aspects of slope stability at the particular location. For now, yes, we have started monitoring the stations by using simple monitoring systems, and I'm sure, as I told you, I'll be coming back with much of this. Apart from this, I just wanted to conclude this particular presentation by giving you the last scope of machine learning. With the data which we are collecting over the time, we are able to look into options of predicting it by using the machine learning. Again, per day, we are getting a data for every 10 minutes from almost like 20 locations at the same 20 stations across the same location. So the data handling will be very difficult. So that's why we have gone across to simplify the data processing by using simple machine learning algorithms, which I can use not only for restricting or cutting off the data or thresholding the data, but also useful for predictions, as well as in order to validate the data which is coming from each of the monitoring station as such. So here we have started with training and testing by using the same concept of 80%, 20%. You can see probably at few locations there are two lines actually, which means that the other places they are overlapped, where we are able to predict the same which is happening in the field slightly ahead. So currently, as per the publication which recently we had, we are able to give a prediction at least 3 days before the slope is happening. We are able to give a very strong assimilation of the fact. But however, as per the discussion with the district administration, they say they at least need 1 week of time to go for a good disaster management option. So that is why now we are still working on getting more data and improving the models itself in order to get a validation, probably a week or 7 to 10 days before the happening of a threshold. So if suppose I can fix up the thresholds in different lines, I can say this is my 60% confidence and this is my 90% confidence. As per the district administration and the requirement of district disaster management authorities, they say whenever we are crossing the 60%, they should be able to start the required activities at the field, and once it is touching 90, then they are at the point. If at all the slope resides or the rainfall completes, or due to any other reasons, if there's any structural measure which is taken care of and we don't touch the 90%, then of course the problem is solved. So we are now currently working in this particular area, and of course when we are talking about all these particular aspects, it's most important for us to come together and start working on this. It's not my statement, but it's a statement which is being made by the United Nations disaster risk reduction framework, which has been given by Sendai in 2018. So it was very clearly said that 87% disasters are mostly looked after the post disaster, whereas only 13% are going on to managing the risk. So when we are talking much about the slope stability analysis and looking into monitoring other aspects, I think it should be much of us to now start moving towards managing the risk and related aspect, which this particular course or this particular session contributes a lot. So again, thank you very much for all of you for giving me this opportunity and taking time to listen to me. Of course, the presentation cannot end with due thanks to all my research scholars who have been persistently working on these particular areas, and especially the collaborators. You can see they are across divisions, including machine learning to image analysis. I am also working a little on to plant root cohesion and related aspects. So I am working with a plant biologist to understand the roots, which again has been very well discussed by Abhiniti. And of course, I'm also talking with Dr. Amit Prasad, who is a person in bacteria. He helps me on working on MICP related aspects. Again, very much touching yesterday's presentation by Professor D.N. Singh. I'm also working in more or less similar areas. Apart from this, of course, I keep getting my help from all my civil engineering faculty, including earthquake, as well as Ashutosh, who is the coordinator of this particular course. So I thank again all of them, including my international collaborators. Apart from this, funding agencies play a major role. They are the one who pushes us to do a good job, as well as keep us on toes when they ask us, why didn't you give an alert before the warning? Why didn't you warn before the particular incident? So they are the one who keeps us in tow, on our toes. So thank you very much again, all of you, for your patient listening. And if at all there are any quick questions, I'll be able to take it. Or you have my email ID, so if you don't mind sharing my phone number, on which you can also WhatsApp me if you have any questions or if you want to do more collaboration. I also would like to take this opportunity to open the stage for any collaboration. I'll be more than happy to put you as a part of my collaboration, and we can do some wonderful job at this particular location in Mandi. Thank you very much.
Thank you, Dr. Uday, for giving wonderful presentation. And yes, definitely IIT Mandi is open towards collaboration, and you could see that the kind of work which we are trying to do. And of course, we always recognize that the challenges that we have in terms of field monitoring, where we have many challenges that Faris has also highlighted. So we, in the tropical region, we face the similar kind of situation. So yes, we all are onto the same page, and we are all here to fight and to strengthen our infrastructure against the natural disasters. So it would be great if we can come together and work together. So thank you very much, Dr. Uday, for giving the wonderful idea of field monitoring and what IIT Mandi is trying to do in terms of monitoring. So we do not have exactly time for taking questions now, and because we are going within the duration of break now, and it is going to end soon. What I would suggest that it is going to be now 4 o'clock in India. So it is afternoon time and 4 o'clock in India. So we will have quickly 5 minutes of break, and then we will start the session. So let us join the session again, where we will be hearing about the numerical modeling protocols. So let us join 5 minutes past 4 o'clock as per the Indian time. Thank you very much to all the participants for joining for this particular session.
Thank you. And also the panel is open in the question answers. So if you have any quick questions, I think we can simply type the answers for you. It's going on. So I'll be more than happy to receive any question from you. Thank you.